So in 1.3, we'll start talking about equations, which means that we're now describing the relationships that we see in our data. The first model that we will talk about is a linear model. So if we can design a linear model for our data that describes the relationship between the x data and the y data that we have, I'm starting with one that should be relatively easy to recognize, right? My x values are 1, 2, 3, 4, 5, 6, and my y values go to 4, 6, 8, 10, 12. Notice that in this table, all of the y values are double whatever the x value is. So we can describe this using an equation like y is equal to 2 times x. So for each x value that we have, we multiply it by 2 and we get the y value that we have. It's consistent. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, and so forth. Generally speaking, our linear models are going to be of the form y equals some a value plus some b value times x. Now, in the example that I just gave you, y was equal to 2x, and so that means that a was equal to 0 because there's nothing being added, and b was equal to 2. To use an example to show how we can determine the values of our a and our b from a set of data where we don't know, I'm using some data on altitude in feet and temperature in degrees Fahrenheit to show you a linear model for the relationship between altitude and temperature as an equation. So in this case, if I'm at 0 feet, then the temperature is 58.98 degrees Fahrenheit. And then notice that the altitude increases in increments of 5,000 for every single one. So I go 0, 5,000, 10,000, 15,000, 20,000, 25,000. This is required to use what I'm about to show you. If your x values do not have a consistent difference, so for example, the data that we used in 1.2, we couldn't use here because there was not the same increase, right? We went from 0 to 1200 and then we went to 2000, and the difference of 1200 and a difference of 800 are not equivalent, so I couldn't use this for that. But I can use it here because it's in increments of 5,000 for each point. Now, what I'm going to do is take something called a first difference, and make that effectively what's sort of like a third column here, but I'm not going to turn it into a column. What I'm doing is I'm looking at the difference in values between the first two rows for temperature. Since I know that this is always 5,000, I'm just looking at the difference between the 41.17 and the 58.98. Specifically, I'm looking at 41.17 minus 58.98. That gives me negative 17.81. Why is that important? Give me a sec. So, if I continue to do that, I do that with the next two. So I take 23.36 and I subtract 41.17. Again, I get negative 17.81. My first difference is negative 17.81 for both. So now I need to do it for all of them. I need to show that it is in fact the same for all of these. When you complete all of your first differences, you'll see that every single one of them is negative 17.81. Awesome. What this means is that the value for our b, the value that goes in front of the x, is negative 17.81, because the first difference is exactly the same for all of the data points that we have. We have a linear model. That's what that means. If they were different, we wouldn't have a linear model. Now, given the form that we have a first difference that is negative 17.81, and we know that we're looking for an equation of the form y equal to a plus bx. Now, given that the difference in the x's is 5,000 for each of these, my b is actually going to be my first difference divided by that 5,000. So b is going to be negative 17.81 divided by 5,000. Because the difference between each of these steps is negative 17.81, and the difference in the x value is 5,000. So the difference in my y divided by the difference in my x tells me what the rate is at which this linear function is changing. So my equation, I get that for b, and then I can get a from the first value. Because I'm substituting in a 0 for x, if I multiply b by 0, I'm just going to have 0. So when x is 0, my y value is the same as my a value, telling me that a is equal to 58.98. So that my equation for the linear model here is going to be given by y is equal to 58.98 minus 17.81 over 5,000 times x, where x, remember, is altitude, and y is temperature. Now that I have the linear model, I could use it to predict what the temperature is at some other altitude, right? So what is the temperature if I'm at 6,000 feet? That's not in my table, but I have a linear model now, and I could use that equation to determine what the temperature should be at 6,000 feet. So if I substitute 6,000 in for my altitude, then the temperature is going to be given by 58.98 minus 17.81 over 5,000 times 6,000. If we simplify this, the number that you should get with your calculator is 37.6, well, it's 608 because of the dividing by 5,000 part. And this is in degrees Fahrenheit. So if I were to ask you to construct a linear model and then tell me what the temperature is at 6,000 feet based on your model, this would be your answer. Okay, the last thing that we'll talk about for this section is an application problem. Yay, word problems! I know they're your favorite. You'll actually like this one, probably. If Sandra buys a pay-as-you-go phone that charges her $1 per call and 5 cents a minute, determine a linear model which describes how much she will pay for a phone call. So you have two pieces of information and you're looking for two constants, right? Since we need a linear model, we know that we're looking for something that looks like y is equal to a plus bx. It's just a question of which one's a, which one's b, or which one tells us what a or b is. Now, if you're getting charged $1 for every call you make, that $1 is a fixed amount. That's an initial cost, right? So that is going to be our a value, because even if she doesn't talk for any minutes, even if she just dials effectively, she's going to be paying that $1. The 5 cents is happening for every minute that the call takes place. So for 1 minute, she's only charged 5 cents. For 2 minutes, she's charged 10 cents, and so forth. And the 5 cents gets added for every minute that she talks. So from that, you can tell that the 5 cents is a rate. The 5 cents per minute tells you that it's a rate, and the rate is going to correspond to our b in this equation. So a is going to equal our $1 cost, and b is going to be the 5 cent rate that she has for every minute. So the linear model in this case, so I'm going to write rate, and this is initial cost. Generally speaking, that coefficient in front of x we're going to talk about as a rate a lot of the time, because it's going to correspond to whatever value x is at the time. Alright, so if we were to write this, we would have y is then equal to 1 plus 0.05x, and the output we know will be in dollars. Now, if we wanted to ask a question, so say she calls her sister and she talks for 20 minutes, then how much does the call cost her? Well, if it costs $1 to make the call and 5 cents for every minute, then the total cost is going to end up being, right, y is equal to the $1 plus the 0.05 times the 20 minutes, because that's a rate per minute. So I just have 20 minutes plugged in. Simplify, you can plug it into your calculator, and you will see that 5 cents times 20 is another $1. So the overall cost is going to be $2 for that particular call. I hope that makes sense. Please let me know if you have any questions, and I will see you in class.